And hey, if you disagree with me, I've given you all of the means available in order to audit what I've done and prove me wrong, so give her a try. So in the previous video, we reviewed the literature regarding minimizing renewable energy costs. Now let's use Python and Excel to show how renewables can provide 24/7 demand using the American power supply. Since I can't find the data resolution I need for Canada. The Aghahosseini paper that I showed in the previous video does the power demand for the total system of North America and South America. American power, therefore, would make up about 65% of that total power. So whatever results we get, we can just divide by 0.65 in order to compare the results to what the researchers got. Using the information that I have, I'm going to simplify the study a fair bit just so that we can get an order of magnitude estimate. I'll be leaving out some key data. As you can see, the researchers used a vast array of energy systems. For simplicity, we're just going to look at onshore wind and grid solar. This will overestimate the results, but we're just looking for the right order of magnitude. To simulate the battery costs, I used $200 per kilowatt hour. To get the transmission costs, I used a multiplier factor of 1.15, which is aligned with the literature on this subject. So all I did was take the energy data from the United States from 2021 until 2023 and toss it into Python to produce some nice charts and optimize the system to minimize the renewable energy costs and ensure that energy demands are met. So let's get into the boring part of the video where I go through the Python code and show you what I've done so that we can reproduce the general results of what these studies are showing. If you're not familiar with Python, that's okay. I'm going to walk you through what I've done and what it means. Then at the very end, I'll do a small snippet of data and show you how you can do this in Excel using the results that I got if you want to fact check me. So we can start right here at the first section. All you do is import the libraries we need and input our constants to show how much installed energy there is in the United States, along with how much power it uses per year. Don't get bogged down too much with it. Pandas just helps you read Excel files. NumPy is for mathematics. Matplotlib is to plot the data. SciPy Optimize is like Solver in Excel. It basically just solves the function. And then OS just allows me to save it to different areas in my drive. The installed power in the states of the different systems you can see here. And this means that we're going to underestimate the earlier timeframes like 2021 and 2022, but that's okay. The max power is important. It's about 1.2 million megawatt hours, but note that the American system uses about 30 to 40% of that at any given time. And then the total power produced is about 4,000 terawatt hours. We're going to use this to determine our battery storage timeframes. So if we want 3 hours of battery storage, it will be 3 hours out of that 4,000 terawatt hours. The next section we have here is the import of data. Basically, the data is split out into 2021 from January till June, and then from July until December. So I'm just importing all of that data. Then we come here and I just concat all the data. I do it individually so that I can see if there's any errors that pop up. Any NA values I just fill with zeros. And then I was running into an issue where the data has commas in it. So I just had to change the commas to a space in order for the system to read it correctly. This little bit of code here is just to determine the columns. This area here, just make sure I index all the data so that we're starting in 2021 and ending in 2023. And just making sure it's the correct date time function. Finally, we grab the data and we drop all the columns that we don't need so that we're not carrying a bunch of extra data through the system. I did 2 cases with this, one that I called df data and then df data adjusted. Basically, the difference is that the raw data set has a number of errors in it. Sometimes you just get insane spikes in energy that obviously aren't real, or you get really big negative values that obviously aren't real. So when I first did the analysis, I started with the df data, but then realized that it's easier to just do the df adjusted, as you'll see a little bit below. That's why I have the df data equals df adjusted. I know it's kind of lazy coding, but here we are. We're able to figure out what energy columns that we care about. And then I just wanted to check the data. So in this commented out area, you can see where I was trying to clean up the raw data by using the percentiles, but again, I found it was just easier just to use the adjusted data. So anyway, we can look through it and just make sure the data looks good. And that's all I've done here. Make sure no values are below 0 because that's obviously incorrect. And then we can print out all of the information to show what's resulting there. So the balancing authority and things like that don't really matter. Total demand just shows us our min and max, how much nuclear power, hydro, and pumped storage are combined together, how much solar, how much wind. We expect the minimum solar to be 0 because at nighttime you don't produce any solar power. Then we can just look at the data in its percentiles. So we can look at the total demand, how much nuclear you get, You can see nuclear is very static because nuclear power plants don't really turn off except for preventative maintenance stuff. Hydro fluctuates a lot more depending on where you're getting power, where you're not getting power, because it's essentially a big battery. Solar just kind of happens, and then same with wind. Except because wind can operate at night, you get a lot more power in the lower percentiles. Then here, I'm starting to figure out how much renewable energy is required to make up this extra demand. So we take the total demand at any given time. This is all hourly data. We subtract off the nuclear adjusted and then the hydro and pump storage adjusted data. And that just leaves us with the total energy that has to be made up by renewable systems. I'm not including hydro and pump storage here because it's so geographically constrained. Then we get the capacity factors for solar and wind. This way, when I add solar or add wind to the system, I can apply whatever capacity factor was happening at that hour of that time throughout the country. And then we can look at the capacity factors. So wind, your kind of median capacity factors around 0.33. And then for solar, it's obviously quite low, but that's not totally a fair comparison because solar has really high capacity factors when it's being operated during peak time, so middle of the day. Anyway, this is one of the charts that I built to show the missing power. I'll show that up on screen. This is my missing power chart, basically just to show how much energy we have to make up with renewables. These are the two main functions. So longest stretch here just tells me how long a period of time do we need battery storage systems coming in? What's the longest period of time that is? And then the battery demand function is kind of the main function that I'm using for this. For the power demand, let's first go through all of the different variables coming in. DF data is the data set that we brought in. Battery capacity is the number of days of battery capacity that we want. Added solar and added wind are the variables that the optimizing function are going to change in order to make sure we never run out of power within this 3-year period, and the values that are going to get reduced in order to minimize cost. Solar cost, wind cost, battery cost, and transmission factor are all shown later, but it's basically just part of the optimization function, and then the transmission factor just multiplies by 1.15. And then the battery capacity is based off the battery time frame that we pick. So let's go through it, except some of the data comes in later because you have to build your functions before you have it. Anyway, basically what this power demand function is doing is saying how much extra wind do we need? So we take the capacity factor and multiply it by the added wind that you go through. This added wind and added solar are the variables that the optimizing function are going to change in order to optimize for not having any power outages across the country, which is obviously good, and having the lowest cost possible. Then our total renewables ends up being your extra wind plus your extra solar plus your original solar and your original wind. Your missing power is going to be the difference between the renewable power and the renewables required, which we calculated before. Then we can get the total renewable and nuclear energy system. So that's all the renewables, all the nuclear, and all the hydro and pump storage. This part here is just so that we don't get a divide by zero error if you want zero battery capacity in one of your scenarios. Then we come down here where I have different variables. So progressing through, I had to make a function for the storage of the system. So I'm just saying that the current storage, we're going to start at battery capacity so that the first increment in our analysis doesn't drive the total renewable cost because you won't have any battery demand to pull off of. And then I look at the energy stored, energy missing, and energy scuttled. So how much energy is storing, how much energy do we have to make up with storage, and then how much energy is wasted because you're going to have a top capacity of energy stored. So this little section right here is what makes this whole program take like an hour to run because I have to go through each individual case and say, hey, do you have extra power? Do you not have extra power? Am I taking from the battery or am I removing from the battery? I can't just do a cumulative sum. It'll take power that doesn't exist. So anyway, this part takes a really long time. Basically, all it's doing is saying the net power of your system is based off of the individual line item of your missing power plus whatever your current storage is. So your missing power could be negative, in which case it'll take from your current storage, or it could be positive, in which case it will add to your current storage. Then I say, if that net power value is above the battery capacity, then we're going to scuttle any energy above that battery capacity, and then energy that's missing within the system obviously won't exist. Versus the other way around, the missing energy will just be the net power. And you won't scuttle anything because you're not losing power from the system. This, of course, is considering a fully integrated grid system within the United States. Then I say current storage now equals net power, and then I clip the results. If net power is negative, well, then you don't have any storage, so that just ends up being 0. And if net power is above the battery capacity, then I just make it the battery capacity value. And then I iterate through saying that the energy stored equals the current storage, and then it goes through line by line by line by line by line for every single case, and then it optimizes on it. Each scenario takes around 80 iterations to complete, so you can see how this part takes a pretty long time. Anyway, once you're completed, you're able to take your arrays and say your stored energy is just that energy stored function, your missing energy is just the missing energy, and then your scuttled energy is just the scuttled energy. The megawatts needed is there to determine how much missing energy there is. So if you have energy that goes below 0, then that's really, really bad. So I just calculate all of the energy below 0. And this is where the minimization function takes care of making sure that is never below 0. I measure the total energy scuttled just for reference, and then I determine how often we have low power. Basically as a 1 or a 0. Are we missing power? Are we not missing power? And then that you can find the longest stretch where we have to draw from our battery storage system. The cost ends up being really easy. It's just added wind times the wind cost, added solar times the solar cost, or battery cost times the battery capacity, and then you multiply all that by the transmission factor, which is just 1.15. And then I return all of this data, the new data frame that has all these extra columns in DF data, the hours max, megawatts needed, energy scuttled, and costs. And then we can put all of this into a test case. So here I got 3 hours of battery capacity, about 2.5 terawatts of wind, 2 terawatts of solar. Using the Lazard study, the average solar cost is about $1 million per megawatt, wind at $1.3 million per megawatt, and battery costs at about $0.2 million per megawatt. Transmission factors at 1.15. And then, like I said, your battery capacity is your total power in the state, so that 4,000 terawatt hour number, you multiply that by a million to get it into megawatt hours, and then divide it by 365, 24, and then multiply that. That gives you hours, and then you just multiply it by your battery capacity. Then you put all of that into your power demand function, and you can print out the results. So you can see in this case, the should be 0 megawatt hours is 0, which is good. That means we have enough energy in the system that we're never going to run out of power in the 2021 to 2023 timeframe. And then the battery capacity was 1.4 terawatt hours. The energy scuttled was pretty high, and the total cost of that was $7.2 trillion. That, of course, is without our 0.65 ratio, so that would go up something close to $10 million for North America and South America. The costs here are still orders behind the economic costs and damage that's produced by climate change, and it's not even optimized. Just look at some columns here. The next two aren't important. I'm just kind of looking at data and information. And then down here, we get to the objective function. So the objective function is going to work with that power function above. It's going to take in the same data. It's going to run the power demand function. And then where we have the important objective is right here. So once we get the megawatt hours needed and the costs out of the function, this is what the objective cares about. How big is that number and how do we minimize it? To reduce the weighting of costs, I divide it by 10 because I care a lot more about us having enough power within our system than I do about minimizing the costs, because lacking power is really bad. Here I have my charts function. This just saves all of the charts into the folder I want to save in, so I can show these results once we get to that point. Then we can just look at the iterative code cases. So below here, you can see my battery cases of 0 hours, 3 hours, 6 hours, 12 hours, 24 hours, 48 hours, and 168 hours, or 7 days. In order to make the function work, you have to seed it with an initial guess. So I do about 0.5 terawatt hours of solar and 0.5 terawatt hours of wind, all the same costs that we described before. And then I also have a data list that uses the timeframes because I found the charts were really difficult to see if you do it any longer than a month. The cases summary is just a blank array that I can toss all that data into. That comes out over here. Anyway, for the function, we look at the battery cases. So you're going to iterate through each battery case. Here, because the 0 case is a lot different than all of the battery cases, I just say if the iteration is greater than 1, then use the results from the previous analysis. But if it equals 1, then you change the initial guess. I just label everything, get the battery capacity, get the result function, which again, we minimize the objective based off of everything. Then we extract the results, get the power demand, etc. All the stuff that we went over from before. This case summary just gives me the summary data that I can put into a nice Excel sheet. And then the date ranges, I'm able to build a chart for each battery case. I know it sounds complicated, but I promise you it's not. Then we can export the case summary, and we can export all of that data. Then we can run a quick check on the data to make sure it works. Then you can see in this case it's $6 trillion. So now with all of our results run, we can look at the charts that were made up from this. I'm going to use a few charts from the 3-hour battery case just to show you what happened. So because we're running an optimization software, it's going to look for a 0 point. So this is the 0 point that I'm showing you. It happened on July 1st, 2021. You can see the battery demand went totally to 0, and then it started to creep back up. But you can see as the system goes through, it pulls battery storage and then replaces it until it caps out at the very top. We can look at the total solar generated, the total wind generated, and then the existing power that's there. So that's the old solar, old wind, nuclear power, and pumped hydro and storage. And then this green line here is that total generation system, and the red is what we're targeting. We can look through a couple more charts to show you how different times of the year have different outcomes. But again, the system, broadly speaking, is trying to achieve stability. And so you can see with this analysis, although it's crude and simple, you can see that we can achieve enough renewable outputs with battery storage that we can easily achieve the total energy demands of the system. Now, obviously, with the paper that I showed, there's a whole bunch of other systems that are integrated to help bring down the total renewables required. But overall, a mix of solar and wind and battery storage and long line transmission can achieve the renewable outputs that are required. So when battery demand is at $200 per kilowatt hour, we can see with 0 battery capacity, we need like 4.3 terawatts of installed wind capacity and 1.2 of solar. And then that comes down drastically as we go through, but the battery demand increases inverse to that. Then in terms of costs, the 3-hour, 6-hour, and 12-hour cases are all around the same cost, trading off battery capacity and transmission. Then obviously skyrocketing as we hit the 7-day case. We can also look at it when we look at the North America and South America case by just dividing by 0.65. We get a similar result, looking like the 6-hour battery capacity is the sweet spot at the current battery prices. What would happen in a case where battery prices reduced by almost 10 times? Now, this isn't a totally out of the world case. There's new battery chemistries coming out all the time. I'm particularly interested in this iron antimony case. This battery solution is coming into production this year, so we're going to see how well that they could scale the system. The total installed capacities are going to stay the same because we still have to meet the same targets. But when we look at the costs, instead of being 6 hours, that pushes over to 48 hours before we get the inflection. And then we get the inflection at 7 days. So you can see how, depending on the price of battery, is going to change whether it's useful to transmit the energy or store the energy. And that's going to get into really interesting economic dynamics of battery companies trying to compete for the lowest cost solutions so that they can buy up all of this extra power that would otherwise get scuttled, and then they can transfer that where it needs to go. And similar to the last case, we can look at it for the North America and South America case to align with the original study. Okay, now let's switch gears to the Excel format. I know for people, the Python format can be scary. It's harder to audit if you're not familiar with the system. So this is the actual data that I was working with. This comes from the EIA, and this is the balance for July to December 2023. You can see the different balancing authorities. These are basically the different areas that manage the power systems. And then you can see all of the data that we looked at in the Python code. I'm going to stick with just the adjusted numbers for this example, but you can do whatever you want. So to align with what we did in the Python analysis, once we get to this analysis tab, I'm just going to look at 1 month of data. So just July 2023. I grab the demand, net generation, all of the other systems. This can be easily done just using a basic sum function. And then we can calculate how much renewable makeup we need to do. Again, similar to the Python code. You take the total demand, you remove nuclear, you removed pumped hydro and storage, and then you find out what needs to be made up by the rest of the system. We calculate the capacity factors, and then we add in our new solar, wind, and the old power, and then add it all together. The constants that I use are here. Wind max and solar max are the same. And then I add 2.6 million megawatts and 1 million megawatts of solar. By doing that, we can scroll down here and get to this chart. You can see the red being the total demand, the white being the new wind, the blue being the new solar, and then the purple being the old power, obviously excluding all of the fossil fuels. And then the green is the total power that we create. And again, you can get a similar chart to what we were showing in the Python analysis. Obviously, this doesn't have like a solver function built into it, and this sheet gets pretty laggy because of how much data is already on it. It's about 46 megabytes for just this sheet. Anyway, I know my analysis doesn't perfectly align with the study that we're providing, because again, I simplified it a fair bit. Overall, it goes to show you that we can meet total power demands just with renewable energy systems. And since they're so cheap, since it's so effective, batteries are getting cheaper, transmission is already a well-established system, renewables are already well-established. I hope this clears up any of the questions that people have around renewable power demands. Even though they're intermittent, they still provide cheap, reliable power. Anyway, in my next video, I plan to tackle some of the new battery generations that will change the curve between transition and battery demand. Thanks for watching. References are all the same as the previous video, but I'll still link them down below. And let me know if you have any questions. And hey, if you disagree with me, I've given you all of the means available in order to audit what I've done and prove me wrong. So give her a try.